I think we took a vacation to visit my family, and I'm standing in the New York subway, and I'm just waiting for the train to come, and I see across the tracks all these marks on the wall, and they were all stationing. It was kind of cool. You're gonna see during the course of the semester, you're gonna start to see stationing marks. You're gonna start to see marks on asphalt around Cabrillo, around the city, on the road. You're gonna just start seeing these things that you never noticed before, because now you know what they mean. So, would I ever report elevation in stations? What does it say up here?
No, because it's only horizontal.
It says horizontal distances. So stationing is only used for horizontal distances. Why do we use stationing? Because I don't want to use huge numbers, right? So instead of saying, well, maybe 177 feet isn't really that far, right? But we're usually talking about highways, interstates, miles and miles, right? What's one, you remember what 1 mile is? 5,200 and? Is it 80 or 86? 80, okay. So if we go a few miles and we're talking about big numbers, right? So the key is, just remember that we're using stationing just so that we could decrease everything by two places. But elevations, yeah, we could be on Mount McKinley and we're dealing with high elevations, but we're still only dealing with tens of thousands. Am I getting that right? Mount McKinley, is it like 13?
I think it's 14.
No,
14?
not McKinley.
20 Mount McKinley?
Yeah.
Wait, I'm sorry, Mount Whitney, I meant
Whitney's like
Whitney.
14.
Whitney's the one in California,
Yeah, 14.
like 14. Mount McKinley is Denali, right?
Yeah.
Okay, so remember that, you have to remember this, because people get confused. Stations is only for horizontal distances. Okay, now we're dealing with vertical distances. There are terms called elevation, datums, and benchmarks. So, do you know what a datum is, or what datum do we use? Oh, we just said Mount McKinley is, Mount Whitney is 13,000 or 14,000. From, what is it measured from?
Average sea level.
Average sea level. Well, that must be some baseline, right? It's the datum. The datum is the baseline by which all elevations are measured from. So we have, this is the datum, and the most common datum is mean sea level, and all elevations are measured from here. You want to take a guess of what the elevation is right outside this room?
200 feet?
Yeah, about 200. Just up that asphalt, it's 223. There's a spot marked out there. So 200, that was good. One time I worked on, does anybody live in Monterey?
Yeah, well, we live in Salinas.
Oh,
Live in
Salinas,
Salinas,
okay,
okay.
Monterey County. So in Monterey, by Fisherman's Wharf, there's this, this rec center for kids and adults. It's a sports center. It's right across Monterey Sports Center. It's right across from the Fisherman's Wharf, and I worked on the soil for that project, and we were dealing with elevations of 8 and 7 and 9. So, okay, what's a benchmark? So Stephen, I know that a lot of this stuff you know, so don't call out, let everybody else know. Oh yeah, datum.
Is datum specifically mean sea level, or is it any benchmark?
Benchmarks are measured from mean sea level.
Okay, so datum doesn't actually refer to mean sea level, but it does.
Yeah, I'm sorry, I'm not explaining it.
It's a
So
model
there's,
of mean
so,
sea level.
so mean sea level is the datum, right?
Yeah.
So when we get an elevation of 200 feet outside here, we're measuring the vertical distance from the mean sea level out there. So a benchmark, okay, so a benchmark is a marker. It's a marker that has the elevation on it. Okay, so a benchmark is a permanent marker. Okay, I always remember which one is the A and the E. That doesn't look right, but you know what I mean. A permanent marker. A permanent marker, I think it's, okay,
It is.
permanent marker.
It's
A and then
Okay, permanent marker that shows the elevation. But if it only shows the elevation, is it providing horizontal or vertical control?
Vertical.
It's only giving you vertical control. So quite often, it also shows some kind of horizontal control. Everybody okay with this?
Yeah.
It might show coordinates, but we'll talk about that some other time. One of the exercises in the class, we're gonna look at maps of Santa Cruz County and see where all the benchmarks are. Okay? But a benchmark is a permanent marker. Usually it's brass, metal. Stephen, have you seen it in anything else?
Yeah, or like just landmark. Or I mean, I've seen it like under manhole covers, with,
Okay.
like an iron. and
Okay,
stuff.
was it a crosscut?
Yeah.
Okay, so in that case, that's really a temporary one. So just to let you know, there's a permanent benchmark, which way is north, north, south, east. East of Cabrillo, there's a permanent marker, and west of Cabrillo, there's a permanent marker. So if the surveyors wanna know what the elevation is at Cabrillo, they have to start at one of those two locations, right? But let's say you have a project that's gonna last 3-4 months. There's no way in hell you're gonna want to survey from there every single time. So what you're gonna do at the beginning of the project is you'll survey from one of those permanent ones, and then you'll put some kind of temporary marker. So when you're walking around the campus, you might see cross cuts in concrete. What that means is they took a file and they they carved out of the concrete, and it's a cross cut. You might see ones that are just written you might see a nail. I'll pull out stuff. There's something called a PK nail. It's a pretty thick nail. The head of it is about 1/2 inch in diameter, and you might see that nailed into the asphalt, and well, they just resurfaced, so we might not be able to see it. But they could put, what?
And the little market flag.
Yeah, those are really temporary. I mean, what I'm trying to do is you go from the permanent to something that's gonna last for a while. The ones with the flags are, they're not temporary benchmarks at all.
There's one out here. There's a cross right here.
Oh, really?
The corner of the building.
Okay, maybe is it right out here?
Yeah.
Okay, so let's go out there at break time.
There's another one that's on Park Avenue, right
Yeah.
next to the on-ramp.
Okay,
It's like epoxy down into the sidewalk.
okay.
There's a little cross there.
Okay, so there was some surveying that was done, and that's where they brought the temporary marker to. So even though it's temporary, it's somewhat permanent, but you can still use it now or still see it.
See,
Okay.
lots of the USGS ones, we tend to come up with any sort of an element.
Oh, yeah, definitely. A lot of
Sometimes
them.
there's like 3 or 4 on the top, which,
In different places.
yeah.
Well, they're probably, yeah. And I think that also helps when you're hiking, if you know if you see benchmarks, then it kind of tells you where you are, and you can kind of set yourself for where you are on the topo.
Yeah.
Okay. All right, let's take a look at the next one, and slope and grade. It's relating horizontal, vertical, and slope distance, and I'm gonna write it over here. Okay, this is very critical, and we're gonna use this throughout the whole semester. And sometimes students think, oh, this is the first section of the course where I need to know these calculations, and then they get to the second section of the course or the third, and they kind of put it out of their mind. But this is very critical because you're actually trying to find a relationship between the horizontal, the vertical, and the slope distance. So we're dealing with slope distance. Slope, if you want to see distance, but sometimes it's not distance. Let's say describing slope. That's not a good pen. Okay, so there are 3 ways. And then we'll talk about when they're each used. So when you're driving on the road going up to Tahoe, right, and you're going up Donner Pass, and then you're coming down, do you notice what sign you see on the road?
6% grade.
The percent grade. Well, they probably have the mileage too. But you see a percent grade sign. Did you notice that you never see a percent grade going up, but you see a percent grade going down? And the reason why is that when it's mainly designed for truckers. When you're going up, you can see the road going up, right? But when the road starts to go down, you can't really tell by looking at it whether it's going flat or it's going down. So there's always a warning on percent grade, down slope. So first thing is percent grade. and it's equal to the vertical over the horizontal, and it's, since it's a percent, it's 100. And the use of this is on roads. When I say roads, interstates, highways,
Plumbing.
plumbing. Yeah, I think so. Let's look at the other two and then figure out which one's gonna start piping. Oh, good,
But
thank you.
Roofs.
Okay, wait, let's go to the next one. The next one is representing the horizontal to the vertical in a ratio. So let's say, I'm gonna give you an example. A 2-to-1 slope. So tell me how to draw that. If it says 2-to-1, if I compare this to this, which one's steeper?
The bottom.
The
Okay,
top
well, let's
one.
look.
The top one.
So this is 2, I'm gonna try to draw the same, 2 to 1, right? That's about that. That's a 2-to-1 slope. This is a 1 to 2 slope. Which one's steeper?
1, 2.
So this is the horizontal, this is the vertical, horizontal, vertical. This one's a 1 and this one's a 2. This is a 1 and this is a 2. You see? So if I wanted to compare these two, and I wanted to use a 2-to-1 slope, what percent grade is it? How would I calculate the percent grade of a 2-to-1 slope? 1/2, because this is h to v times 100. So what's that? A half times 100, 50.0%. We ever gonna see that on the road? No. But what might we see a 2-to-1 slope on?
A mountain.
Okay, a mountain,
Stair. Well,
Bills?
no, never mind.
hills. How about, think of driving though. When sometimes do you see a 2-to-1 slope? Maybe going up a mountain, right? Going up the embankment. Let's,
2 to 1 or 1 to 2?
remember we talked about,
1 to 2 or 2?
either one. Remember, we talked about fill? So let's say I have this, this ground surface that looks like this, and this is what you do to denote ground surface. So you want to put a road in there. So what are you going to do? You're going to say, okay, I want to balance cut and fill. Remember what cut and fill is, right? Cut is taking soil out, fill is putting soil in. Why would I want to balance cut and fill on a job site?
So you have
I don't have to haul dirt off and I don't have to bring dirt. Because not only do you have to pay for the dirt you buy to bring to the site, you have to pay for any soil you remove, and you also have to pay to rent the truck and pay the person to drive it. So you want to balance cut and fill. So let's try to balance cut and fill. I'm going to put my road like this. So this represents fill and this represents cut. Hopefully that doesn't look, how about that? Does that look about the same area maybe?
Yeah.
sure.
Yeah.
Okay, so here's my road, right? These people are driving in, so remember on an arrowhead. Have you seen this before? This isn't civil engineering. Have you seen that mark? And then let's put a C over here. And then have you seen this? It's like an arrow coming at you and an arrow going in.
Right.
Have you ever seen that
I think
before?
25, isn't it?
No, I don't think it's anything technical. Did Karen use it in that class? I don't think it's technical at all. But this is like an arrow coming at you. You see that the tip of the arrow and the round wood part of the arrow. And this is, you're seeing the feathers,
Right.
okay? So the cars are going into the board on this side and the cars are coming out of the board on this side. Okay, so in this case, if this is the road and they remove all this, they're probably gonna put a retaining wall here to hold up the soil, right? But there's some embankment right here. That's called an embankment. And there's a steep drop off right here. Here's another embankment. So when we deal with the H to V, we're specifying, just like percent grade, we're talking about a road. H to V, we're talking about an embankment. So those are the two uses of those.
Can you clarify?
Yeah.
That little notch you put out, but how's that little notch?
This thing right here,
Yeah.
so I'm trying to show that here's my V and
Oh, I
here's
gotcha.
my H.
Gotcha.
Here's my H and here's my V. This might be, I mean, it's gonna be the same slope because it happens to be, I drew it the same, but maybe you might have a steep slope here and then a road and then a more gradual. So you might have a different, you might have a steeper slope, okay?
Okay, thank you.
And, you know, when you're at the beach, if you have dry sand and you pile it up, there's always this one, it's called angle of repose. It always falls down at a certain angle, I think it's 45 degrees. I think, I'm not positive. But if you imagine, I mean, we could talk about adding water, but let's not add water. How about if you had clay? If you took clay, could you get a steeper? You could get a steeper, right, steeper embankment, right? So what determines what you have to design is based on the type of soil. So if you have sand here and sand here, or sandy soil, probably not gonna have sand unless we're in, except Marina, you know, when you drive to Monterey on the right side, it's all dunes, right? And I also worked on a project where we put the, part of the bike path in, you know, that bike path that goes from Marina all the way through Monterey, I don't even know how far it goes. But that's all sand, but typically we have sandy soil or clay soil, that's gonna specify what type of embankment, H2B that we can have, the type of slope we can have. Okay, and then the third way to describe slope is really not used for civil engineering at all, but it's more mathematical. So if we have the tangent of an angle, so let's draw our triangle. Here's my angle, I'm just gonna call it alpha. The tangent of the alpha is, what's this distance represented as? V, and this one, horizontal, is equal to V over H. So then you could say the vertical angle is equal to the inverse tangent of V over H. So these, when I'm putting boxing in green right now, are the three ways to represent slope. And you need to make sure you know those. Yeah, Allison. Yeah, tangent inverse. So if tangent, it's a way of writing, it means angle who is. So
Yeah.
the angle whose tangent is V over H. It's just a little negative one. Have you seen other notations?
Arctan.
Oh, arctan, ARC-tan. So if you look now, I'm gonna pull this down. If you look at the packet, I got a hold of this sheet a while back, I think it's pretty cool. Let's turn it around. So the whole sheet is showing slope equivalence. So let's zoom in and see if we could read one of these.
There's nothing else.
It's not.
Oh, sorry. I do that a lot, so you'll have to keep telling me. Okay, so it's showing slope equivalence. So it's showing all three of those, percent grade, H to V, and then the angle, the vertical angle. So let's zoom in. Why don't we zoom in on the 2-to-1? So here's a 2-to-1 slope. Oh, can you see that? Here's a 2-to-1 slope, H to V. It's also equal to a vertical angle of 26 degrees, 34 minutes, and it's equal to a 50% grade. So if we did the math over here, so if we have the angle is equal to tangent, the inverse tangent of V, if we use the 2-to-1, V was 1, right, and 2. Tell me what that comes out to be on your calculator. Give it to me in decimal degrees first. 26.5? Somebody else get 5?
Yeah.
5, 6, so let's say 6. 26.6 degrees. But now one of the things in homework, you had to learn how to convert from decimal degrees to degrees, minutes, seconds. Degrees, minutes, seconds. And what did it come out to be? So on your calculator, you should have a button that says degrees, minutes, seconds, or it has a little notation like a degree symbol, a foot symbol, which is minute, and an inch symbol, which is seconds, and this is usually the button. But if you have those more complicated graphing calculators, then you have to figure out if that thing is embedded somewhere. You need to know how to change these back and forth. So make sure you're comfortable with that, because it'll hold you up on a test. So 26 degrees, how many minutes?
36.
What did you get?
36?
Say it again?
36.
36? Did you just say 0.6 times 6?
I said that times 60.
Okay, but you don't want to do that because this is rounded, right? That's the
Oh.
problem with decimal
Yeah.
degrees.
Okay.
So start from here, 1 divided by a half, a tangent inverse of a half, and then convert it to degrees, minutes, seconds. 26 degrees. I think they only have,
33.90.
okay, wait, so 33, so 0.9, so it's 33 minutes, and now you have to take the 0.9 and multiply it by 60 again. Say it again?
I got 36.
Oh, did somebody else get 36? We just need 2 people to confirm.
I got 54. 54 seconds.
This,
We both got 54 seconds.
Me too.
Inverse tangent.
We got 26 degrees, 33 minutes, and 54 seconds.
Okay, 26 minus 26 equals times 60. 30 degree, right, minus 33.
Normal calculators really have degrees, minutes, seconds?
54.
Oh,
54?
it does?
54 seconds.
Right, good.
Yeah.
Finding it takes
That'd be
a while.
And
nice.
had I put it in,
I don't have it though, I think.
okay, anyway, I don't know, I just do it now.
It's a little.
All right, and then let's take a look at what we see here. 2 to 1, 26, 34, and then rounded up. But this is kind of a cool thing to have.
Just realized that we're doing radians. So
Uh-huh.
like this.
Z will like that. He likes radians. Okay, I think we need a break, huh? Okay, 15 minutes. Come back, look at the clock. Allison? You guys are gonna have to help each other because you all have different calculators and I'm not, no, so you can't, this is correct, but this answer is not exactly rounded, remember?
Does anybody have an
Wait.
HP?
Yeah, wait, no. Go to inverse tangent.
An HP,